Hi, my name is Alan Nguyen. I'm a senior at the University of Hawaii in the Electrical Engineering program. For my 496 project, I worked on exploring liquid metal plasmonics. First off, what are liquid metals? So liquid metals are elements that are in a liquid form at or above room temperature. So from the 118 elements on the periodic table, there are 5 we can narrow it down to: mercury, francium, cesium, gallium, and rubidium. Of those 5, there are only 2 that we can work with, because francium is radioactive, cesium and rubidium are explosively reactive. So that leaves us with mercury and gallium. Why are liquid metals and the research on liquid metals important? With liquid metals, there is a possibility of designing tunable electronics. Imagine being able to manipulate the size and characteristics of a device after deployment. Another is the development of flexible circuits. Circuits that don't need to be absolutely rigid expands the possibilities for electronics. With their unique characteristics, there are some downsides to using liquid metals. Mercury, for example, is toxic. Gallium likes to form an oxide layer as soon as it comes in contact with oxygen. This oxide layer prevents direct contact to the metal. Another thing is that the conductivity is a magnitude lower than that of copper. Copper has a magnitude of 58.5 times 10 to the 6 Siemens meters, compared to Gallium, which has 3.46 times 10 to the 6 Siemens per meter. The focus of my project is on the plasmonic response of Gallium, an alloy of gallium, indium, and tin. But what is plasmonics? Plasmonics is the study between free electrons in a metal and an electric field. An easy way to imagine this is if you put a metal in an electric field. The electrons will move to one side and the positive ions will move to the other. Once you remove that electric field, they will be attracted to each other again. That oscillation as they are moving towards and away from each other is the plasmonic response of that metal. Plasmons are the quantization of that oscillation, like phonons are quantizations of mechanical vibrations. The University of Utah conducted an experiment on the plasmonics of eutectic, gallium, indium, another alloy of gallium. The results from their experiment showed promising results in the plasmonic response of eutectic, gallium, indium. The focus of this project was to conduct the same experiment as the University of Utah did, but using Gallium instead. From the results, we can see the plasmonic response of Gallium and potentially start working on tunable electronics using Gallium and possibly graphene. The first step was working on recreating the mode that the University of Utah used in their experiments. We decided on making a few changes. We determined that the size of the apertures shouldn't matter, but the periodicity does. So we scaled up the design to have 1mm apertures and 2mm periodicity. We also shortened it from the 15x15 array to a 10x10 array. To make the mode, we decided to use Kapton tape and Silhouette Studio to draw and cut out the modes. We cut the modes out of 6 layers of Kapton tape. This part of the process was the most tedious and exacting because it was easy to rip the tape. We then put the cutout Kapton tape onto the bottom of a petri dish and used PDMS, a silicon-based polymer, to create the mold. To make the PDMS, we had to mix a pre-polymer and a curing agent in a 10:1 ratio. Upon mixing and pouring, we put the mold inside of a vacuum for 2 hours, or until there was no more bubbles in the mixture. We then cured the PDMS in an oven at 80 degrees Celsius for 20 to 30 minutes. After the PDMS mold was removed from the oven, we let it sit for 20 minutes to cool down. Next, we removed the PDMS from the petri dish and then delicately removed the Kapton tape, making sure not to tear any of the PDMS inside the apertures. The last steps in creating the mold was to seal it using another piece of PDMS and a Corona plasma treater to seal the 2 pieces together. Next, we injected the mold with Gallium. We had to be careful not to get any sodium hydroxide into the mold, as it would cause Gallium to beat up. Gallium is kept in a sodium hydroxide solution, so it doesn't oxidize. The design and manufacture of our mode took up a lot of our time, so we weren't able to set up an experiment to test the plasmonic capabilities. For future work, we would like to conduct terahertz time domain spectroscopy. Terahertz time domain spectroscopy is used to probe the characteristics of a material with short pulses of terahertz radiation. With these results, we will understand the plasmonic response of Galenstan, which will help us get to our goal of designing a phototransistor using Galenstan and graphene that will be tunable after manufacturing the device.